exercise I would like you guys to show. That statement 1 implies 2, implies 3, implies 4, implies 5, implies 1. And hence, they're all equal. Okay. Finally, let me take this statement 5 and work with it a little bit more. So remember, if I have F, some vector in the Hilbert space, and the basis set, the basis of ER, then taking the inner product of ER with F is basically taking the I basis vector and dotting it into F. Right? So let me just give you some intuition for this. So imagine I've got some vector F, and F has components F1, F2, Fi, etc. Okay? The I basis vector in a finite dimensional Hilbert space, or in finite dimensional vector space, the I basis vector is that vector that has zeros everywhere except in the ith entry. Okay? Now what we do when we do this is we take that guy and we take the column vector and we make it into a row vector. So this is a row vector with zeros everywhere except the ith position where it has a 1. Okay? So when I multiply these two, row vector and column vector, it's 0 everywhere except when this one multiplies this guy again. So this singles out for me the ith component of the vector F. Okay. So what are we saying when we write down the norm squared of F? Well, what we're saying is F in a product F. And what that tells us is that this guy is equal to the sum from I equals 1 to infinity of EI F. You can prove this exercise, this guy, but this guy is just the I component of F. So this gives me then sum 1 5 squared, sum from I equals 1 to infinity. This is the quality version of what we wrote the last time, which was Parseval's inequality. So this is called Parseval's quality. And the statement in here that I can take the identity matrix and expand it by summing over all of, by expanding of the outer product of the ERs, right? That's what this is. Not inner product, which is row times column to give you a number, but column times row, which gives you a matrix. Right? That's called the outer product. This statement here, that if I sum over all the ERs, I get the identity matrix back. That's saying if I take these guys here, right? These are the EIs, just move the one around, and I multiply them all, I'll get a matrix that has a 1, zeros everywhere else, a 0, 1, zeros everywhere else, a 0, 0, 1, zeros everywhere else. If I add all of those guys up together, then I get the matrix that has 1s in the diagonal and zeros everywhere else. All right? So this is what's called the resolution of the identity. Because it's allowing me to take the identity matrix or identity operator in context of this course, and resolve it into a particular basis. And what this allows us to do is whenever we have inner products, for example, we can insert an identity operator between the column and the row, and then expand that in this set, and that allows us to, for example, write down something like this. Okay? So by now, I hope that all of you are at least somewhat familiar with the fact that the set of continuous functions on some interval A to B forms a linear vector space. Right? You typically work with polynomials. So when you did linear algebra, for example, in the second year, they would have told you about polynomials in X, right? And you would wonder, why are you talking about polynomials? And of course, linear algebra. Well, that's because I can add and multiply and subtract polynomials. And the fact that I can do that tells me that they form a linear vector space. Right? So the set of, and then I can expand functions, continuous functions in polynomials as per Taylor series expansions. And if I can do that, then the set of continuous functions on an interval from A to B form a linear vector space. All right, so the set of continuous functions on interval from A to B form linear vector space. But this linear vector space is not complete. So the question is, what does it take for us to enlarge this space to make it? And the reason I want to do this is because I want to take as proxy for most of the things that we're going to do in this course on operators. I want to take as proxy for a Hilbert space set of something continuous functions. I say something because I want to take a set of continuous functions and then enlarge that space so that it's a complete vector space. So we want to work with functions and operators on functions. Right? So when we talk about differential operators, those differential operators act on functions. The functions are the vectors in the vector space. So I need to tell you then how to construct vectors in that vector space. So I need to take the set of continuous functions of A to B and then enlarge it so that it forms a complete vector space. Makes sense? So an important set of functions in the space of all functions are those that satisfy the following inner product. And here I'm using a mixture of the kind of typical functional notation that you're familiar with and the vector notation that we've been building up to talk about vectors in the Hilbert space. So suppose I have two vectors in some space. I'm going to define for you what that Hilbert space is just now. F and G. And I'm going to define the inner product between these two vectors, F and G, to be the integral. F and G are continuous functions on A to B. So I'm going to define it to be the integral from A to B of G of X complex conjugate times f of x multiplied by some weight function, just because I don't quite know what the measure I'm using at this stage is, so I might as well. So just to unpack this, means complex conjugate. This is a weight function. That I don't specify just yet, but I don't really care. Eventually, when it comes to that point, we will specify something. In most cases, you're familiar with W equal to 1. Okay. So if vectors G, F are equal, then this means that I have a way of computing the norm of the vector as the integral from A to B of mod x squared. That's just f complex conjugate times f as a function. W of x dx. I'm not guaranteed that these integrals are going to converge. I'm not guaranteed that these integrals are going to be well defined. Depends on my function, depends on weight function, etc. But I can look at this and say that for those integrals, so for those functions for which those integrals converge, well, let me say that better. Those functions for which these two integrals converge and are well defined are called square integrable functions. That's because the square, then mod square, is an integrable function and the integral is well defined. Okay. So those functions for which integrals 1 and 2 are well defined. Are called square integral functions. And the set of all square integral functions with weight w, that is to say, when I define the integrals defined with this weight function, is denoted by L squared omega on the interval domain. The set of such functions is L squared w on the integral from A to B. Right, this is called a set of square integral functions on A. Yeah.
So it's which there are defined and there exists another vector for which it is defined or been defined for all bit. So which for example send square integral functions or functions for which 1 and 2 are defined. So that just mean that they are square integral in relation to one another.
Yes.
Okay. So it's not objective.
I don't mean that the functions are defined, I mean that these integrals are converged.
Yes, correct.
Right. And to be clear, when I talk about these integrals, I'm talking about the integration that we're doing is what's called the Begg integration. It's a generalization of what you're probably familiar with, which is Riemann integration. The distinction is not really relevant for what we're going to do. Lebesgue integrals are fantastic. You have super discontinuous functions. Lebesgue integrals allow you to treat those functions with lots of discontinuity that Riemann integration doesn't capture. But it's a generalization. I'm just keeping it as general as possible. And for all the functions that we're going to be working with, Riemann integration is perfectly fine. In other words, this type of integrals you're comfortable doing. That is, if I give you some function f of x, you draw the curves of that function, you split the area under the curve into rectangles, you sum up the area of the rectangles, and you take the limit as the width of the rectangles go to 0. Okay, that's Riemann integration. Lebesgue integration is you do it with horizontal rectangle. And that allows you to treat functions that are discontinuous. Okay. Okay. I should tell you a little bit about some of the remarkable properties of the set of square integral functions. It has a number of remarkable properties. I'm not going to list all of them, but I can tell you what two. First is that it is complete. Which is great, but that's what we want. And the completeness statement about the set of square integral functions, sometimes in the function analysis literature would go under the statement of the Riesz-Fischer theorem. So pretty strong. So that's something. Yeah, that's what it is. The second point is that all complete inner product spaces with countable bases, all complete inner product spaces with countable bases are isomorphic to L2. So this is important because what it means is that when I deal with functional spaces that are that have an inner product and are complete, we might as well just work with elsewhere, a set of square integral functions, because all the other ones, any other ones that you can think of, are isomorphic. Okay. All complete inner product spaces. With countable bases. So what this does for us is it takes the kind of abstract notion of a Hilbert space, which we've been talking about and kind of alluding to the fact that our intuition is guided by what we know from finite dimensions. But it takes this abstract notion of a Hilbert space and it converts it to something concrete, like a function space, because you guys have been dealing with functions since day one, basically, right? So you know how to do things with functions, you know how to do calculus with functions, you know how to differentiate, integrate. So we can define operators on the space of functions, right? And because of these properties, I know that the things that I learned from studying these function spaces are the same as the things that I'm going to learn by studying a more abstract notion of Hilbert space. Okay. So let's make this even more concrete and consider the sequence of monomials. So these are going to be some eighth power of x, where k goes from 0 to infinity. Right. My claim is that these guys form a basis for this function space. And then this establishes two things for us. The first of which is that any square integrable function I can then expand in terms of these monomials. Okay, so any square integrable function I can write as f of x equal to the sum, and k equals naught to infinity of some constants, let's call them alpha k, x to the k. Okay, because these form basis for the set of square integrable functions. And two, L squared is a separable Hilbert space. That's the same thing I'm using. Yeah, right. Yeah. So the first thing you might consider asking is whether this is an orthogonal basis. Yeah.
Reciprocal always mean tangent equals global space.
Sorry.
Reciprocal always mean that we are tensor just global space into individual case.
That we are what?
We're using a tensor product.
Tensor product.
Yeah.
That's separable always being tensoring. No. So okay. So separable in our context it means that the basis is going to be countable. Right? So even if I have an infinite number of these basis vectors, they're not going to be a continuum. And I'm going to be able to count them.
Like a Fock space.
Like not necessarily.
No, Fock space.
Oh, yes, the box space is an example. That's right. I want to make one more point. Let me make one more point and then we can stop for the day. Which is that. You are used to working with orthogonal bases, right? So if you think about R3, for example, the I, J, K basis vectors are orthogonal basis vectors. In the sense that if I take the dot product of any two of them, any two separate ones of them, I get 0. And if I take the dot product of the vector of itself, then I get 1. Okay. The set of monomials, on the other hand, is not. Okay. However, you would also have learned in first Boston linear algebra that given some set of vectors, I can auto-normalize that set of vectors by the Gram-Schmidt algorithm. Right, and you can do exactly the same thing here with these with the monomials, and I'll end up getting some polynomial set that is orthogonal and spans L squared. Okay, so we can or orthogonalize, let's say orthonormalize the set of monomials by Gram-Schmidt. To get a set of orthogonal polynomials I'm going to call C. Okay, let's say Cn of x, where n now goes from 0 to infinity. Whose span is L squared. And given our definition of what the inner product is, in other words, it's written in terms of this weight function, then it should be clear that whatever orthonormal set we're going to get is going to depend crucially on your weight function that you use to define your integrals. Okay, so different weight functions will generate different orthonormal sets, and this is precisely the orthonormal polynomials that you might have encountered, like Hermite polynomials or Legendre polynomials and all of these things. They're just defined by different weight functions in the integral that you use to define the product. Make sense? So let's stop there. And what I want to do next time is explore some properties of these orthogonal polynomials and what they mean for the Hilbert space that we're going to be working with this set of square and right.